Okay, welcome. So we're here to talk about a droid's journey. This is our experimentation with mruby using that inside of Go. So my name is Chase McCarthy. You might know me on the internet as Code for Fun. I've been having a lot of fun here in Japan. Recently dressed up like a samurai. So yeah.
Hi, I'm Terence. I go by Hone02 on Twitter. I work for Heroku. If you deployed a Ruby app on the platform, you probably used code that I've written. We both come from Austin, Texas. We like to say we're the capital of awesome tacos. If you're ever visiting Austin, we'd be more than happy to take you out for some tacos and show you this delicious food. I also run a conference in Austin called Keep Ruby Weird. Believe we're throwing one this fall, so if you're in town for that, please stop by. This conference talk started around last summer in August of 2017. This kind of, droid company called Sphero announced an R2-D2 droid. And so these are the R2-D2 droids that they've come out with. And I was pretty excited for this because I've been, since a kid, I've been a big Star Wars fan growing up watching a bunch of the old movies. And this R2-D2 droid, based on the trailers, seemed to be like one of the most impressive replicas that they've had, both with lights and sounds and movement and like tripod and bipod and things like that that you'll be seeing in the talk today. And I want, and they had also like a phone app that you could use to control it. And Sphero historically has enabled you to actually like programmatically control the robots that you're buying. And so I was really interested to be able to do that, but with Ruby. So like, how do we go about and kind of doing all this stuff? We want to be able to write Ruby programs to actually control these robots, in the language that we love. And so we started exploring what it looks like to actually program robots in general, unrelated to the Sphero stuff and what's out there. And I think the most promising thing and most prominent one is this project called R2 by the Hybrid Group. And they have some support for some Sphero droids, but they only support Bluetooth Classic. And unfortunately, all these Star Wars robots use Bluetooth Low Energy, or BLE. And basically, since September of 2016, since there isn't really good BLE support in Ruby, they haven't been able to actually like make the BB-8 robot, which came out in 2015 work, or was 2016 work. And so we couldn't really go about and get this to work that well. So we started looking at this project called GoBot. And it's also done by the Hybrid Group, but it's a library for controlling robots with Go. And one of the things that was kind of the big differentiator for us was that it uses Go BLE, which is a Go implementation of the BLE library, and it only works on Linux and OS X, but allows us to actually control these robots. So they actually have built-in support for controlling BB-8. So if you go to the web page, this is kind of the sample code that you're going to get. Just being able to go through and then change the colors, the LED colors inside the BB-8 robot itself. And just going quickly through this, the first thing you have to do is instantiate this new robot. And it takes basically the connection that you're going to go through to interface with the robot. So in our case, we're just going to establish a new BLE connection and then pass it into this new robot function. And then the next thing you have to do is instantiate a BB-8 driver that you're actually, or whatever driver you're using to actually control the robot itself. And then finally, you define some function that you want to actually have the robot execute. And then you pass that in, and then when you click start, or call start, it will actually go and execute whatever code that you're telling it to, connect to the robot, and actually run it. And we'll show a quick demo of actually just running this thing in pure GoBot. So here's the camera. And I guess you can kind of see that on the screen there, but it's going through and just picking random values for RGB and sending those and then just lighting up the colors. And so this is just an example of GoBot actually using BLE and controlling the BB-8 that we have here. But unfortunately, they had BB-8 support, but there was no R2-D2 support. So we can actually go ahead and control the other two droids that we have up here.
All right, so the first challenge we had to tackle was like where do we start with something like this? Like how do you get information about what APIs are here? Like we said, these APIs weren't made public. We know that they're slightly different from the Spheros, but we kind of know what company made it, so we expect that they're a little similar. And we know that they're Bluetooth, and that's basically because if you don't have Bluetooth on, the app doesn't work. So they at least tell you that much. We know they're Bluetooth low energy also because you don't have to pair with them in order for them to be found. Just some terminology real quick. The BLE we've already mentioned is Bluetooth low energy that was introduced in the 4.0 spec. The GAT I might refer to later. That's just a generic attribute. So a few of the things we'll be talking about are considered attributes, which just means that they have a value you can read or write or both. And generic attribute just means that they're kind of like a plugin for BLE. So what all we need to know about these to control them? First, we need to know what kind of services they offer. From the docs for Bluetooth, services encapsulate the behavior of part of a device. I think of them like a collection of data and associated behaviors. I think I pulled that from the website. It's not a quote from me. But basically, it's just like what can this thing do? But services are kind of higher level. You can think of them like a service on a server. So you might have multiple services. You might have multiple instances of the same servers. But each one of these services has their own API, which is the actual functionality they can do. And those are called characteristics. You can think of those as like the API of the service. They're the endpoints, what the specific things you're doing. Like if this was a thermostat, it would be temperature. And you might have a set, or you might have a read. All right, so how do we find the services? And right now I'm going to go through a quick set of things that I did to figure these out. Some of them failed, but I wanted to mention them because if you go about trying to do something like this, you're probably going to fail a lot. And that's just kind of normal for the Bluetooth space, and you'll see why. So the first thing was to just use BlueZ. So if you're on Linux, you can use BlueZ. It has a bunch of command line utilities, has libraries that you can, and headers that you can link to and make, C, or I believe there's some Python libraries that use this. And the stack is pretty stable, but the one thing I found out is the command line utilities are not necessarily so stable. The one I use all the time, though, is this HCI tool LE-scan. So if you have your computer out right now and you run this in this room, it'll just blow up with all the Bluetooth devices here. And so if we were running it right now, we would see something like this, where we see the D2 is R2-D2. So the left is the MAC address and the right is the name. There's another tool in here called GAT tool, which if you try to use, or you see some blog posts from years ago where people were using this to connect, you might think you could just do this, which is you run GAT, you give it the MAC address, -i's, and an interactive shell. When you drop into that, you just type connect, and then when you get in here, it'll say connected successful, but after 10 seconds or so, you'll get a big warning, or a big error, and it just crashes out. And basically just every device I've tried does this. And on the internet, everybody's just saying this is just how it's been for the last few years. It's kind of in a broken state. So sadly, we can't use this. So the second attempt was Bluetooth sniffing. So I have a couple of these little devices lying around of different makes. And this one's pretty cheap. It's like $25. You can see BLE traffic. The one problem I ran into with this is that it doesn't decode encrypted traffic. So BLE adds encryption, and all of these have an encryption built in, although it's not really that secure. So if you get a better device, you can actually get around that encryption, even with just a sniffer. But I didn't want to go buy another more expensive device, so the third attempt was kind of a man-in-the-middle approach. So if you think about what's happening, the phone kind of sees the BB-8 here, and the BB-8 says, here's my services and characteristics, and then the phone sends the commands, and the BB-8 responds with, okay, I did that. So like a man-in-the-middle thing is kind of like, you broadcast to the phone, like, I'm a BB-8, and the phone says, okay, I want to connect. And then you like send that to the BB-8, and you say, I'm a phone. And then you just sit there in the middle kind of logging data or manipulating data. The problem with this is if these devices are really close, they can still see each other. So if you're trying to like change the packets, they'll get kind of confused and they'll end up dropping a connection due to some error. So a more complicated approach, which I got working, was to separate them by some distance and then proxy them over the internet or just on a LAN. And this works, but it just seems really complicated, right? Luckily, there's a tool that does this. It's actually pretty good. VTL Juice is I think pretty much all JavaScript. Uses Bleno and Noble, which are the JavaScript equivalents of some of the libraries we use. And I was able to get this working, but it just seemed like way too much work, especially since, as we'll see coming up, we had to kind of iterate on these over and over and over again, and this is a lot of work to set up. So luckily, there is a better way. Took a lot of exploring around because it's not very well documented. But if you have an Android, this works on 7 and below and 2, but it changed recently, so that's what I'm going to go over. If you enable Bluetooth snoop log, then your phone will start recording all the Bluetooth traffic. Now, the problem is like, how do you get it off of there? So when you enable that, you go into the app here, connect to one of the devices, it starts to make some commands. And at some point, when you've sent the commands you're trying to figure out the kind of payload for, you go back into the developer settings, and you can say, take bug report. And that presents you with this dialog. You click full bug report, and click report, and it just goes away, and you're not really sure what happened. But then like a couple minutes later, this little notification will pop up. So it's saying it's saved off. And when you tap that, you'll get like a link to share it wherever, Dropbox, or in my case, I saved it to Drive. I just wanted to show you what the folder structure is. So it's a lot of data, about 22 megs of data zipped. But then if you drill down into this folder structure, you end up at this BT snoop log. And something we really got lucky with is that Wireshark works out of the box with BT snoop logs. So if you just open this up, it'll detect it and it'll find it. So here's one of the examples, and you can see the way I found this was that Pixel 2 XL is my phone, and I know the MAC address and the name of the device I'm looking for, so I know that's commands my phone is sending. There are some that are the opposite, like you see below it. The things we're looking at here are the service UUID, so this is the unique identifier for that service. The next thing is the characteristic ID. So this is the actual like command endpoint that's being used from that service, which there will be multiple of these. And this last part is kind of the part where the real meat of it. This is the data. This is the actual payload that goes over. So if you do this over and over again, and you capture a bunch of these, which is kind of hard because you have to figure out which one's which, you'll end up looping over, doing it over and over and over again, and getting a big list of them. And then you just have to kind of look for patterns. And again, Sphero, in this case, had a little bit of documentation on their older stuff, but most of this has changed. One thing we can look at here is all those are the same, so we don't really care about that. After looking at a bunch of these, you can see that this first column here is all just a sequence, so every command you send just increments a sequence. And that's, I think, basically just to prevent replay attacks or something. The next one here is kind of is the real part of it. And this is a very small command, so this is only 1 byte, but this could be many. So in this case, you can see that 1 maps to tripod, 2 maps to bipod. This last column wasn't so easy to figure out, but it's just a checksum. It's called mod 256, so you just add up everything between the brackets there, modulo it, and then invert it, and that gives you the last column. So if we do something like this using GoBot, because we don't want to just do this in pure Go, because GoBot exists, we'd like to be able to contribute back to this. So this is the implementation of the R2-D2 driver, and most of the stuff up top is just internals of GoBot, but the name, the connection, and the packet channel are the things we really care about. You can see, as an example, the tripod function there is just writing out to the packet channel, and it's just crafting a packet. And it's using a couple values that are kind of hard-coded there, but those are the CID and DID of that type of command. That's just something that's fixed. And in this case, you can see tripod it just writes a 1, like we saw. 1 means tripod. Craft packet's a little more complicated, but it just basically wraps like an envelope around the whole payload, calculates the checksum, and then sends it, returns all the bytes so you can send it out the channel. So we're going to play a quick demo of this real quick. So this is just using raw GoBot. So we didn't do this on the table just so you can see the console output clearly, but it's basically, you can see those values are the same values we saw on the table. So it's calculating them, the droid is putting the tripod out, and then pulling it back to a bipod, and then going back and forth. So we know we're right in this. So you kind of have to do this for every single thing, every light, every macro, everything you want to control.
So now that we got all this stuff working with Go, we're wondering, is Go like the only option here? Do we have to do all this stuff with Go and not be able to use Ruby? And when we were looking around, we figured out that there were really like two options here, right? We could either write native extensions in Go and then basically pull that into an MRI program. But we kind of decided against that. Like, there's a lot of prior work with mruby and robots. MRI today, like if you use R2 at all, like there's definitely, like, and you talk to Ron Evans, like there's some limitations with kind of like highly evented architectures doing that with R2 and MRI itself. And then in addition, if we want to actually package or distribute kind of a binary for this thing that we would share around, that becomes much more challenging in MRI itself because there aren't ways to compile it down into like a single file that we can hand out. And so then we started looking into, well, mruby exists, there's active development on it, I had some experience working on it in the last few years. Is there a way we can actually embed mruby inside of Go and actually use it? And some of the benefits that we got out of this is we can leverage all of Go's existing concurrency primitives like Go routines and channels, kind of higher level, and then have that kind of orchestrate all the mruby VMs themselves. And then both mruby and Go also have packaging initiatives as well. Like you can build a Go binary down to single binary, and then especially if we're embedding mruby into it, mruby can basically be compiled down to a single library file that can then be linked against and embedded in, which would allow us to actually have a single binary that we can distribute. And so doing some research, we found out we didn't actually have to kind of build that stuff ourselves. Mitchell Hashimoto actually has a library in Go called Go mruby that actually takes care of kind of doing all this stuff for us. And so here's a simple hello world of going through how you actually go about and doing that. And so just quickly walking through this, the first line here actually just spins up a new mruby VM. And so all this stuff is just Go mapping stuff around the C mruby API. And if you're not familiar with Go, there's actually a special keyword in Go called defer, which is kind of like ensure in Ruby if like the whole method was wrapped in a begin block. But basically this will ensure that it gets run at the end of the function. And so we want to make sure we're closing that mruby VM here. And then continuing to use the mruby C API, we're able to then define a class. So in this case, we're defining this example class. And then we're going to attach this class level method add on it. So this function is just adding two numbers together. You pass it this Go function and the second argument of like what the actual functionality is, and then finally there's the number of arguments this method in Ruby is going to take when we actually call it from Ruby itself. And then jumping back up, here's the actual definition in Go of that function. So every mruby function has a special signature that has to be defined. So the first argument that you're passing is the mruby VM itself. And then the second argument is kind of the object that this method is being, like the self-representation of this object, so you can then refer to it inside the function itself. And then mruby as a function then returns two values, the first being the return value of the function, and the second being if there are any exceptions raised, you can then return that as a return value here as well. And there's a getArgs function to then fetch the arguments, which are just mruby values. And in our case here, we're just going to take the arguments that are being passed through, convert them back into Go, add them together, and then convert that Go value back into mruby, and then return that. And then since we're not raising any exceptions here, we're passing nil for the exception as the second return value. And then with that, in the mruby VM, we can actually just load any generic string of Ruby code, and we're able to then call the function, and you'll see if you actually run this program, that will return 42. And so that's like how you can actually like instantiate and execute an mruby VM inside of Go itself, which was kind of one of the first building blocks to actually get some of the stuff running. And luckily for us, Go mruby actually handles a lot of the build process here. The only real extension we had to do when building the libmruby.a was mruby allows you to use an environment variable called mrubyconfig, which allows us to then customize our mruby, so we can set any kind of gems or dependencies that we want, set the compiler, set like target platform and things like that. In our case, we're adding some stuff like random and sleep just to have that available for controlling the robots. And then the rest of it, Go mruby actually handles. So it goes in vendors, mruby in its own library. It builds it based off of your buildconfig.rb, and then it copies the libmruby.a into a folder that it knows of. So when you actually go ahead and do a Go build, which is the command you run to build your Go project, using cgo, it actually knows how to link against libmruby.a, and so then it has access to the mruby VM and kind of all the things that you need to do around the cmruby API. And with that, you get a resulting binary that has mruby embedded into it, and you can actually run it.
All right, and so the next step was to figure out what kind of API did we want to use. So we have to basically define a bunch of top-level classes that you can instantiate and call methods on. And so we called this D2. So we had a couple of goals with this. One was that we wanted somebody who's using this library to really only have to be able to write, or only have to write Ruby. So you shouldn't have to drop into Go and do a bunch of, and learn Go and know how to build Go. It should all just be in Ruby. But it should be extensible, so you should be able to add, like we showed, the mruby gems, or add Go packages, and maybe create a new driver for something else if you want to extend it. We also wanted the ability to coordinate multiple tasks. So the whole point of this was to be multi-threaded and completely concurrent. So we want to be able to run multiple robots at the same time, kind of under one umbrella, or have them communicate. The other thing is we wanted for this to be pretty small, which we sort of achieved, but there's still a little bit of work to be done with the Go side of it. mruby's pretty small, but Go adds a lot of things that we simply can strip out. So I want to run real quick through an example. This is the R2-D2 if we were to want to just spin the dome, kind of in a sweeping motion. So the first thing we do is we instantiate an R2-D2. We give it the name that we saw in that LE scan. The second thing is we just, in this while true loop, we just keep calling dome, passing in the new heading, and then it's just sweeping them back and forth. So if we run this, where do you have that? Right, so yeah, you can see that it's just sweeping back and forth forever, so just sitting in a while true loop. So, yeah. I try to kill that.
Yeah, so going through the architecture of actually how all this stuff works with the program and library that we wrote that we call D2. So the first thing that we're doing is we're actually starting up a bunch of workers for every mruby file that we're creating. And so I'm going to go through kind of this chart step by step in a few sections. So when we start up a worker, we actually go through first, and there's a CLI program that we execute where you pass in all the mruby files that you want to run as scripts that will get executed. And so that's what is happening here. And then for each one, we're actually going to spin up a new Go worker for us to actually go ahead and do that work and spin up mruby VMs and whatnot. And then similar to like in mruby when you're doing threaded stuff, like at the end, if you don't actually find a way to either block on the thread completing, the program will just exit because like these things are being spun off separately from the main program. So we're using a wait group inside of Go to kind of handle that. So once all the stuff is done, or you hit Control C, we will actually then finish and close out the program. Inside of start worker, we're using add to basically tell the wait group that, hey, we want you to wait for this thing to finish before we go ahead and do stuff. And then go is just syntax in Go, if you're not familiar, that actually spins up a new Go routine. So you can pass any function you want to Go, and that'll spin it up in a new Go routine there. And then similar to the Go mruby example, here we are in the worker, just spinning up a new mruby VM that we can now use to kind of control the robots that we want. And again, when this function closes, we want to actually close the Ruby VM. Going back to the picture, we actually need to make all the kind of classes available in Ruby, so you can actually call functions on R2-D2 and make like the DOM rotate, for instance. And so that's kind of the next step that happens here. So we go through and call these Go functions specific for each droid, and actually define these classes in the mruby VM. And what that looks like here, it's very similar to kind of the Go program that we saw before for Go and Ruby. We're going to define a class called R2-D2 for the R2-D2 case, and then we're going to define all these methods on it that you can now use. So these are, unlike the other one, these are actually define method defines instance methods on top of that class. When we call DOM or tripod like before, it will actually go and execute those things and correspond to the corresponding Go functions. And then finally, inside of the mruby case, when we actually call R2-D2 new or do things inside of mruby, these are things that happen in the constructor here. So the first thing that happens after you actually define the stuff on the VM is that we go ahead and process the mruby script itself and then execute that in the mruby VM. And the moment that you actually call .new on it, you're passing kind of the unique identifier handle of that robot itself. And this will actually then kick off a custom constructor that we've defined in Go for that. And the reason we have to do that is because all the kind of BLE stuff we were talking about with Go needs to happen when you actually connect to the robot. So we need to do that inside of Go and not in Ruby. And so this happens here where we just set up a new BLE similar to like the BB8 thing, and then we're going to set up R2-D2 instead of BB8. So we set up these connections, and we're able to then work with the robot. And then, before with the RGB stuff for BB8, we had this kind of extensive work function that did all that work. But in our case, we need to actually use a wait group again here, which is separate from the other one, to basically wait to do any of the mruby execution after new until the robot's actually ready to receive commands. You're not sending commands off to the robot until it's actually ready. So this work function, once it executes, we now know it's ready to actually do work. So that's what this work group here does. And with that, once we have that new stuff running, we can actually now execute functions and send commands to the droid itself. And so we're calling .dom here, and then here's a kind of chart of how that actually works. So when we're calling .dom from mruby on top of the R2-D2 class that we've defined, it actually goes through and executes all the Go stuff underneath. And so we've defined that DOM method from before, and we're calling this DOM function that we've defined inside of D2 to kind of wrap the mruby stuff around GoBot. And so that's what this function looks like here. So if you notice, this function signature looks basically the exact same as the function signature in the Go and Ruby case, because this is just an mruby function inside of Go. And then on this line here, this is where we're actually calling the GoBot driver to actually execute the thing and send the packets. And so if we pop into GoBot inside the R2-D2 driver, we can see this is what the function looks like. And when Chase was talking about the craft packet and saying those packets, this packet is what we need to send to actually get the DOM to rotate.
So one of the other challenges we ran into was managing multiple Bluetooth connections. Like we showed, we can't just go create the Bluetooth connection like on startup because we haven't loaded the scripts yet. We don't know what robots you're going to try to new up in Ruby or what the names are. But we needed a way to manage those connections, because when mruby calls back in to Go, we get like a self context of what object is being called on. But we didn't have a way to store some like Go native things on that object. And so the strategy we came up with was basically just to create a table. So this is just kind of doing a table lookup based off of the name of the connection to find the driver you're talking about. So that looks like this. You can see we're storing, because it's typed, we're storing a BB8 driver and an R2-D2 driver map. The R2Q5 is the same as R2-D2, so it just gets stored in there. So the other thing that this does is it passes the table into all the start workers. So when these get started and when the new R2-D2 gets called to build up its method list, it gets that table too so that it can use it in initialize. So inside of initialize, now when the droid driver gets created, we store it off in this table. And the idea is that we can look this up later now when a new method gets called on this new mruby object. The other thing we had to do was currently there's no Go mruby support for instance variables, and so we kind of just did this little trick to just reopen the class and define an attr access over name so that we can use that later to pull out the value, and there's another place where we set that value. And that's how we look up this driver. And this driver function, like I said, gets called in every, dome, move, all the other commands that we defined. Everyone has to call this first in order to get their BLE connection. So now we're going to do a kind of final demo of all of it working together. And you can see what they're doing here is they're mirroring each other. So they're both running the same command, but just opposite. But they're running all within one file, and it's controlling multiple BLE devices.
So that's a bunch of work that we've kind of done to actually get all this stuff working with only writing Ruby code to actually control the robots at the end. And we'll post up what the actual demo for this final thing looks like, and it's not a lot of Ruby code to actually make that happen. So kind of the stuff that we're looking for now that we have kind of it running is that we're talking about kind of the single binary packaging story, and one of the things we want to do is actually the ability to actually take all of the mruby scripts that you have and compile them into the lib mruby.a that gets linked against from Go. And so that allows you to not have to have these like mruby scripts around. I mean, you do lose the ability to kind of write that stuff on the fly, but we want that to be an option, to have a single binary that allows you to then connect to robots and not have to deal with kind of all this other stuff with it. The fact that both Go and mruby do support cross-compiling, maybe not together yet, but we want to see if we can actually create a tool for D2 so we can cross-compile binaries, so you don't even need to run Go build or do any of that stuff locally to kind of just get started and running. And then finally, right now there isn't a way to do communication between the different robots or files, and so we want a way to leverage Go's channels to basically allow you to then communicate across multiple files, because you may have multiple files controlling a single robot. For instance, like R2-D2. The R2-D2 and BB8 have collision detection because there's an accelerometer in there, and potentially you may want just one file controlling kind of motion collision detection, and you may want another thing to like spin up a light based off of that, or what have you. So it allows you to kind of do more complex interactions, and those are kind of the directions we want to take this project next. But yeah, that's kind of all we had. This is the GitHub repo for our project. So if you want to go there, you can see all the source code for all this stuff. And thank you.